Hey, Vijay. Morning.
Morning.
I saw Ramya wasn't going to join. Are you able to hear me? Can you hear me?
Now I do. I
don't hear you actually. So something's up. Better now.
Do you hear me okay now?
Yeah.
All right, good. Let's switch to my headphones actually.
Yeah, I saw folks were complaining about the times, right?
Yeah, I was thinking that, we have, like some people show up, during this time, but it's usually just, 2 or 3 or 4 people at most. So I know like we have other people who wanted to join as well.
Mm.
And so I'm just throwing it out again, seeing.
Where are you, Vijay?
I'm in California, Los Angeles area.
Oh, okay. Okay. So I really like the the concept that I'm actually getting to read a book, which I wouldn't have otherwise. So if people and more people it's possible, it's more comfortable for them to join, then we can probably move it to the evening. I can work with that too.
Yeah, exactly. Because if the study group ever is like, let's say, you're not there and Srini's not there, then it's just me, like for the most part. So I I just want to be careful.
Yeah. Okay. Yeah, I mean, we can propose the evening times, not weekends because they're very unpredictable. But other days, maybe evenings, I can work around as long as we have a schedule and all. I can kind of move things around.
Okay. All right. Sounds good. 11. What time is it for you right now, Srini?
It's 10:30.
10:30.
In half an hour. Yeah, 10:34.
Okay.
Okay.
All right. Okay, so I'm gonna share my screen and get my headphones stuff all set up.
Yeah. So the today's we will be looking at probably graph models. It's a total new area for me. Yeah, let's start.
Okay. All right. Do you still hear me okay? Just wanted to ask.
I can hear you. Yeah.
Okay. All right, cool.
Can you make this Kindle screen big?
Yes. Yes, I can. All right. Okay. Everything good now, right? No technical difficulties.
Yep.
Okay, perfect. So last time we talked about MapReduce and also imperative versus declarative. This has been a pretty long chapter. So we finally made it though to graph-like data models, which I think is the last part of this chapter.
Mm-hmm.
So basically just kind of jumping in, right? Graphs, how many of you know what a graph is?
I know.
Oh,
okay.
You nice.
I know, that's it.
Okay.
I didn't work. Yeah.
All right. When somebody says graph, are they talking about like an X by Y coordinates graph, or what are they talking about here?
So my understanding of graph is in couple of ways, right? One is through the social networking use cases, and the other is through the Graphql kind of API data model.
Yeah.
So yeah, I see the primary use case for graph as the author clearly articulated very well here is if the data model itself has many-to-many relationships, and you have very complex many-to-many relationships. So graph model is I would say it's an extension of relational model, because you still talk about relations, but the main attribute or the main characteristics of a graph model itself is relation, and that too not a simple relation, but a complex relationships itself. So the implementation itself, the underlying foundation principle itself, a complex relationships, and they solve that problem very well in graph-like data models.
Yeah.
How is it
Good
different from the
points.
hierarchical ones, right? Like at the beginning of the chapter.
Yeah, that's a very good way. I was about to say that you see some relations between hierarchical and network model in graph. They are same, but through the evolution, they're better. They're solved in much better way.
Okay. Right. Yeah. So that's what, like in the end of the chapter, he says this is the greatest of the databases. At the beginning of the chapter, he says this is the worst.
If you remember, that's why I told you, right? Reading about this evolution provides you a lot of insight and how the technology is evolving and how architects are, redesigning their stuff, and how the opinions are being changed and how the use cases are being changed.
Yeah, in fact, actually, the summary of the SQL, basically the previous MapReduce thing, right, was that you can actually implement SQL kind of a query on top of NoSQL databases, and that's actually faster than traditional ways of implementing SQL is what.
Yeah, but there are so many middlewares, especially in the data lake and data warehouse area, where you have a lot of middlewares. It doesn't matter how you store your data model, but they give interface for NoSQL APIs, REST APIs, or relational.
Yeah. Yep.
Yeah, very good points. Coming back to the main question, right? A graph is very much similar to a tree, right? And a tree is hierarchical in that it has one parent and then children, and then each children has its own children. But children usually have just one parent, whereas a graph, you have two parents or more parents, right? Which is more true to life. We all have two parents, I think, who made us. Whether they live with us or not is different, right? But yeah, in a graph, like it's more unstructured, whereas a tree is structured. You have, children, you have leaves, you have branches, whereas graphs, they can just kind of go in multiple directions. So an example of a graph that is really popular is Facebook, right? Everybody probably knows what Facebook is. And so, yeah, like they have the Facebook Open Graph, which, I think that's their API. If you ever wanted to explore this, right, this will kind of allow you to take a look and see, what kind of data is out there on Facebook, right? I'm sure some of you already know about this, but you can kind of get data on who Jane Smith might be, and then who her friends are and when her birthday is, and go down a rabbit hole essentially of information.
Oh, they expose that as like you can just make curl calls and get all the data.
That's right.
Oh.
I mean, if you have a Facebook account, you can register your application and get the client ID and secret to query this.
Right.
Even Microsoft, all of their APIs, they're changing from REST to Graph API model. If you look Office 365 or even public cloud APIs as well.
I didn't know that either. That's something new to me. I'm a very poor user of Facebook anyways, but
well, that's the thing, right? There's so much data now, right? And they said that data is more valuable than gasoline, right? Can you imagine that? And so if you control the data, you basically control the world, right? And an example of that is, how Facebook has so much data on everybody that politicians want to get in, on all that too, and influence elections, right? And so you might say that you're for, the Democrats or something like that, and if you're in the US, but then like if they know that about you and they know that you change your mind a lot, they can put a whole bunch of ads in front of you to make you think the other way. Oh, you say that you support the Democrats, but did you know that they do this, blah, blah, blah. And they'll just nonstop bombard you, right? Till you change your mind on the election day. So it just depends, right? Like, again, how you use this data, but this data is very powerful if you have access to it, which the big tech does. And that's kind of why they're called big tech. So yeah, in any case, right, like this is kind of like gigantic. It's like bigger than trees, because trees like MongoDB and stuff like that, still easy to kind of, search through. For the most part, if you keep a tree, very structured, where it's, well, like if it's prioritized, or if it's like in a binary format, like where you can search easily, a binary search tree, right? Then it's easy to kind of find like information pretty fast. If you remember your big O, right, then it's O log n, like if you're searching down a tree. But if it's a graph, it can take a long time. So there's a lot of tricks to search a graph. But just kind of going through my highlights here, right? If your application has mostly one-to-many relationships, a tree is appropriate, right? But if you have many-to-many relationships where everybody's your friend and their friends are your parents' friends or whatever, and it just goes on in like a big circle, right? Then it's more natural to start modeling data as a graph. And graphs still have edges, right? And vertices. Vertices are nodes. If you think about the data structure, like linked list or something like that, it's the same word, but they just changed it to say vertices for graphs. And sometimes, like I was telling this to Karthik yesterday, I think like when you're learning data structures and algorithms and doing this stuff, I think the hardest part is just understanding the vocabulary, because it's extremely, it changes a lot, right? And sometimes it's extremely dense. So just catching up to that. Any questions so far? All right.
No, it's all good.
Okay. Yeah. So one of the well-known algorithms for operating graphs is, finding the shortest path between 2 points on a road network, as well as the page rank, right, which is Google's algorithm to determine the popularity of a web page. And this is actually one of those system design questions, although it's a lot harder. But I don't think anybody's asking you to build Google's page rank algorithm. I think it's just more or less like, could you give kind of like a basic explanation as to how this thing works? Is anybody familiar with PageRank here?
No.
I'm
Okay.
not, but that's not true. People do get asked to build Paxos algorithm, CAP theorem, and stuff like that in system design. Probably not at a senior software level, but once you go principal engineer, yeah, they do ask.
Yeah. So it's something, to kind of think about, right? Like, how do you, index the web? What kind of like algorithm would you use? So I'll make a bookmark here. Is this something to come back to and, maybe study together? Especially as we start to finish like reading the book or whatever,
Mhm.
But yeah, just basically like some other examples, right? Like web is also a graph, right? And Google is constantly like crawling this graph of pages, right? Like each page has a link, and then that can link to other pages, right? But other pages can still link back to the same website, right? If you're familiar with the term backlinks. And so it's no longer a tree, right? Like it's no longer there's one source of truth. It's really like you can follow links to pretty much anywhere, and they can all kind of come back to each other in a circular format. So being able to navigate that is kind of like a nightmare, unless you're Google, right? Which is basically why they're the richest company in the world. They figured out how to do it. And then of course, real life is a railroad, so again, like just kind of 2 points to kind of throw in here. Just remember vertices and edges when you're talking about graphs, although vertices are nodes, and edges, like are basically the lines in between the vertices. So here I made a note too that Facebook maintains a single graph with many different types of vertices and edges. Vertices represent people, locations, events, check-ins, and comments made by users. Edges indicate which people are friends with each other and which check-in happened on which location. So here's kind of like a diagram. Lucy is a vertices, Alan is a vertices. These are their edges, right? So Lucy and Alan are married. Alan is born in another vertices, but this is a city. And then this is within a department in type a region, inside a country, inside a continent. And so you can have many types of cities, countries, regions, states, countries, continents, right? So this essentially is a graph. So the next part is pretty much about like, well, they're going to start to talk about, like how to traverse a graph. Does anybody here know the difference between breadth first search and depth first search?
I mean, yeah, I mean, can talk about it, but like, do they really talk about that, or are you reading a different book?
I'm just asking questions because like I think graphs are interesting. Like,
Okay,
like,
okay.
the most interesting. Yeah.
Yeah.
And
Yeah. So the breadth first search is basically traversing all the you handle it by levels, right? You basically traverse all the immediate child nodes, and then come back to the first one, and then traverse the second level stuff from there. And the depth first search is basically going all the way, like you basically handle it from it's the others. So you can correlate that with the queue and stack concept, right? So what does it say here?
yeah, so you're on the right track. Like, so breadth first is kind of like, in my mind, right? Like if you have like a whole bunch of like vertices to go through, right? You want to kind of take a shallow approach to looking at each vertices. You want to just kind of go and essentially find like the shortest path to the end. So, depth first search, on the other hand, is kind of like exploring each node and then like its children and then its children and its children and going all the way down to the end, right? And sometimes if the graph is very long, like a linked list, again, it can go all the way down to infinity. And so like you might be stuck in a depth first search for a long time. And so like they say that if that's the case, then, like you probably don't want to do a depth first search first. You probably want to do a breadth first search. So let me see here. I want to get a different
Because breadth first search was more I would say horizontal, under the same parent, right? First level, first child.
That's right.
and covering everything, but depth is more child's child and going way down the whole tree.
Yeah, you might hear the expression that going down the rabbit hole. Sometimes I hear that and I think, oh, that's a depth first search, you know, like just going down. Like
Yeah.
I have all these pages that I have on my Google Chrome, right? And to me, breadth is like going across and just reading each one like this. Whereas like depth would be exploring like every single link in here and just like reading. So this would take obviously a lot more time to kind of explore. Like, so I kind of like these terms. I think it's useful to know that.
Yeah.
And, you know, it might help like understanding like what a Neo4j or a Titan or an Infinite Graph is doing under the hood. Because I'm pretty sure that they're using these kind of algorithms. That's kind of like my point. Like, how do you explore a graph? There are two common ways. And then there, of course, there are more ways to explore a graph than the basic algorithms. So, yeah, so let's go on. There are three declarative query languages for graphs: Cypher, SparkQL, and Datalog. Does anybody have experience with that? Okay. That's all right. So
I think only who uses it, right? Like maybe people who are actually, yeah, maybe people at Facebook. I don't know any other company who uses them. But yeah, I don't see any application in my business, like the product I work on.
to
Do
be
you guys see the application like in your work?
So to be transparent, right? I feel like this is kind of like even new for me, right? Because like I've definitely never used Neo4j, but like I think it's interesting. That's the only reason like I'm actually thinking about it. You know, and I did always kind of want to know like how these things work, you know, on an intuitive level. I hear that a lot of this stuff is important for today's machine learning, right? A lot of people who are into that are very interested in understanding like big data, like altogether, right? And so they're using these kind of bigger tools. So it's a very specialized field. It's definitely not your web developer or, you know, front-end software engineer, or even like back-end, like traditional REST API. This is more just like beyond that. Like this is where if you start doing graphs, I'm pretty sure that the job that you might be applying for might expect that you have a master's degree.
Yeah.
It may not be like that they require it, but they definitely want to see like that you understand these tools, you know, because it is specialized computer science.
The question is like, do we need to understand the graph algorithms to actually use these tools? Like, can we not take the SLAs that these query languages and DBs provide, and just, okay, whenever we have this kind of you know, many to many relationships, can we just not, you know, let's not solve the algorithms part. Let's just take
Yeah.
it.
You're absolutely right. Yeah, like nobody wants to do that. No one wants to do the algorithms part. I mean, like that's kind of like, again, it's the specialized part that people get hired for to create, you know, like the algorithms, and then the write up a spec so that we can create the software to make it easy on the front end to kind of just use the tool, right?
Right.
Forget like graph, right? Even any even SQL and stuff, right, Amulya? If that was a requirement that we had to know algorithms, probably I wouldn't have a job at all, right?
Yeah.
We just use everything as abstracted. That's why, you know, that I'm pretty sure like there are like a lot of PhDs who are sitting and writing these things, right? We are never gonna make something even better than what these guys have collectively done, right? So yeah, that definitely will not be a requirement, but understanding it, yeah, right, to be able to use it effectively. So maybe about almost 10 years ago, while I was consulting in one of the gigs, so they were using graph database Neo4j specifically, but how they arrived at it, like I never got to understand that, why they chose that. They were building recommendation systems like Expedia, but it never at that time, like I could never get into how the decision was made. But I think it's mostly how people feel, because in today's world, NoSQLs bring the same power and stuff like that. So people who are more data scientists who want to see visually these things, they were using it, Graph. So I don't know if that makes sense. Just for analysis purpose and stuff like that, like tools like MATLAB and stuff like that.
Neo4j is a very popular graph data model implementation in the market.
And it's open source, right? All open source are popular. Generally, people get their
I think they have
hands on it.
commercial version as well.
Yeah,
Look
yeah.
at this.
Yeah.
It's pretty crazy, right? Blazing fast graph, petabyte scale. So you have petabytes of data and you can still like traverse this graph like super fast. This is kind of like how it goes, right?
Yeah, a lot of people use it. Really, I'm pretty sure there is a lot of interest in graph. Maybe just that we haven't touched base on those groups or have experience in those areas who are using it. But it's in real world, it's being used for sure.
Mm-hmm. Here's kind of like how the Cypher language looks, right? And then compare that to SQL, right? So it is a little bit more like
Yes.
abstract, shorter. It's definitely a learning curve, but like
how do they give any performance benchmarking results or something to say this is some?
Oh, I'm sure. I'm sure. Like trying to do this kind of query in SQL probably would take a really long time, whereas this Cypher query is probably optimized, right? They even say graph optimized query that understands and takes advantage of its connections. So I guess we can play with it at some point. And I advise people that, on this call and watching it to just kind of definitely check out this thing, maybe even just kind of take a free course if that's available, see what Neo4j is. Even if you never end up using it, just kind of for fun. Who uses Neo4j? Well, airlines, insurance, banks, retailers, it's pretty big. Okay, so coming back to here, we have property graphs. And so in the property graph model, each node or vertices, right, vertex consists of an ID, a set of edges going out, a set of edges going in, and a collection of properties, right, key values. So if you were to create like your property graph class, you would have ID, then you have edges for outgoing and edges for ingoing, and properties that you want to store as key values. Each edge that is the connection, right, contains an ID as well, and the vertex at which the edge starts and the vertex at which the edge ends. This is called the tail. In fact, I should highlight this. And then the head, right? And a label to pretty much describe the relationship between the two vertices. So, and then it also has a collection of properties. So it's kind of like a bigger data structure. You just kind of have to wrap your head around it. Here they kind of have the SQL like for this, so you can kind of see like an example. Vertices again has a ID properties in terms of JSON. So you can see like JSON part is the stuff we already know, right? Like that's the hierarchical model, but that's like inside the properties. Then we also have the edges, right? And then this has the tail, the head, the label, and the properties. Again, this is JSON. The rest are just integers or text. So a graph stores consists of two relational tables, one for vertices, one for edges, as shown in this example. And this is using PostgreSQL. Then important aspects of the model is any vertex can have an edge connecting with any other vertex. There is no schema that restricts these kind of things. Given any vertex, you can efficiently find both its incoming and outcoming edges and traverse the graph, follow a path of chain of vertices, both backward and forward. So again, kind of like a linked list, right? Like you're kind of going from head to tail, and you can, I guess, like in a graph, like if you don't really know how far it's going to go, it could probably go on. This is actually, again, like why I keep hammering on the data structures, algorithms things, because like, it helps to just kind of know this like side by side. Like, so if you're like thinking about how long or how fast this might take, you can apply the big ON to that.
Yeah. So one easy thing that we can probably research is are these databases optimized for read and not for write? Is that the assumption that this, because if you have so many edges, traversing them and updating them, doing so many writes, I don't think the data can be even is taking advantage of a locality principle either, right? Because your data, basically the information is scattered across the graph. So I would think that it's not optimized for write. But yeah, it's that's the call out for the hierarchical database they had mentioned at the start, right?
Mm-hmm. Yeah. Does anybody want to answer that, or we can just hold it as a question, I guess?
Yeah.
To research.
Yeah.
Okay.
I can just read up about that and update in the hacker.
I think it does write well than read. In the sense, because the information is not really scattered, because the information that you're going to bury in is linked to some kind of a parent always. Let's say, for example, employees in your org, right? There is someone who's leading the org. You always can find ties under that. If a new employee joins, it's always hooked up to it. In this case, right? There is always connectivity to it. So the same way how LinkedIn or linked list we do, if we do the algorithmic way, writes like, put add and this thing is not expensive. Traversing it and deleting it and reshuffling it. The minute you delete it, then sometimes it reshuffles it under the child and stuff. That is the part that's expensive.
It takes a long time.
But again, that's an interesting question. Maybe I have to think a little bit more. But I thought it's good for write than read.
Yeah, I don't know. Yeah, I don't know the nuances. I have to read, but yeah, I can take that action item and yeah.
And you have to remember too, like these are not simple like linked lists or simple like data structures underneath the hood. These are like highly optimized and prioritized, and like they have different algorithms that probably know how to like keep track of like items like by ID or items by like index. I guess this is partly why you create this structure in the beginning, so the optimizer can go and find it for you and return it for reads or writes. But just like Karthik is saying, when you start trying to delete or you try to like alter, that's probably when it gets more expensive and takes more time. But yeah, just coming back to this, right? Like there's a figure 2.5. So let's see here. 2.5. Probably help if I actually click the link. Let's do that. So I'm going to click this link here, and this is 2.5. Okay, so going back to where we were, the figure shows a few things that would be difficult to express in traditional relations schema, such as different kinds of regional structures in different countries. France has departments and regions, whereas the US has countries or counties and states. And, this kind of makes it kind of difficult for doing, like the traditional relational databases because that can get hairy. But you could also imagine extending the graph to exclude other facts like Lucy and Wayne or other people. You could indicate any food allergies they have. So ultimately, like a graph is basically like the reason people or companies use graphs is just really because like you can just like add as much as you want, right? Like information as you want. In terms of data, it is unstructured, but that's kind of like the charm point of a graph. Graphs are good for evolvability. As you add features to your application, a graph can be easily extended to accommodate changes in your application. So contrast that again to like, you know, what we saw with JSON or what you saw with like SQL, right? And, you know, again, hierarchical versus relational. Those may be a little bit more difficult. JSON probably is a little bit similar in graphs that they can also evolve kind of quickly, but when you have more of a structured database, that's probably not as easy. Cypher is a declarative query language for property graphs.
Hey, why are there no edges in that vertex definition, right? Like he says in a property graph, you should have edges also. Like in the previous page, in the vertices definition, there no, in the page you were
Next
on.
page. Okay, here.
Why aren't like how is he going to keep track of edges if he's not storing them in the vertex data here, right? Here you are supposed to have edges also, right? Like otherwise, how are you? So vertices are the actual the data holding piece, right? So and you're supposed to have the connections to
Maybe here.
different edges. Yeah. Oh, so tail vertex integer references vertices vertex ID. What's that doing?
Yeah, head and tail are the head is where you connect the head point. Vertex is what you connect to the parent. The tail is connects to the child. So this is like he's building a DAG kind of algorithm, not like, you know, top-down tree structure. Right? Head and tail.
So are you so each vertex will only have one incoming edge and one outgoing edge? Is that a constraint somewhere?
Yeah, that's the one that is talking about here. But graph database doesn't fit into that. In graph, a particular object could be connected to multiple on the side as well, horizontally. But here, for simple representation, he's just building a simple top down. Yeah.
Okay. So but ideally you would. So the vertex can have multiple incoming and multiple outgoing, right? Yeah. Okay. In that case, you would want to represent that in the.
Yeah, that's the complication in graph, right? It gets really complicated at some point.
Okay.
Yeah, but this is a good question. I'll also just kind of look at this in more detail. I think this is how he's doing it for this example. Okay, so here we are at Cypher, right? Anyone watch The Matrix? Does anybody know what that movie is?
If I get paid, I watch. I don't understand. Yeah.
All right, it's only the most popular movie in America, I suppose. Like maybe around the world. I don't know. Like for I guess Generation Z, maybe you haven't seen it. But yeah, just basically Matrix is that fun movie, I guess. And Neo is the main character. So Neo 4J was kind of like why I guess they were fans of the Matrix, and so they liked that and they decided to use that for the name. Cypher is basically a language similar to the SQL syntax, but it's meant to help like traverse graphs. So they use this kind of syntax here. And I guess like we can kind of read it, but like, you know, just more importantly, I think for this part of the chapter is just to like go through it and like understand like, you know, what Cypher is like and how to they
how
use
the
it.
query looks, right?
Mhm,
So
mhm.
basically, how are you, the query language uses verbs like within. Basically, you define the kind of relationship, and you can just name it anything and just look for that kind of relationship between edges between the vertices.
Right, right. So yeah, I mean, like here they kind of tell you, right, each vertex is given a symbolic name like USA or Idaho, and other parts of the query can use these names to create edges between the verses. So Idaho within USA creates an edge labeled within,
Mm-hmm.
and then Idaho as the tail node and USA as the head node. So I'll just highlight this part too as well.
Mm-hmm.
Create North American location in North America, and then location United States, inside location Idaho, state, then Lucy is a person. So Idaho within USA within North America, Lucy is born. So this is how they're creating that query to, add a vertex. When
if you ask questions like who immigrated to, let's say, USA, not USA, right? Like it's the middle of it's the USA vertex is somewhere in the middle of the chain, right? Idaho, North America, and like USA is in the middle. So now you need to go there to the USA vertex and then trace back to all the cities within the USA. How do you even find where USA is, right? Like if you just ask, get me people from USA, how do I know where is USA? Yeah, I think that's where you need to understand the algorithms.
Yeah, basically, right. Like they start off this part of this chapter, like by saying, like with any kind of like software like this that looks at data, I think the most important thing, and I remember this from like a course I was in, is just being able to ask questions, right? Like if you ever go to like an SQL interview or something like that for a job that's primarily SQL, they'll give you like questions, right? And they'll say, show me how to do this in SQL, like this English question, convert that into SQL. So I think that's kind of like also the basis like for, using new software. It's like, I want to do this thing, like I want to find out like all the people, born outside the US, for like in Europe and migrated to the US, right? So it's kind of like what you have here, this little line. So if you were to think about this in SQL, how would you write something like this, right? And so if you start thinking about it, it probably is going to become pretty complicated. But I guess that's also the same question you have like when you have a different software like Cypher, right? So here they kind of like talk about how to use their query, and it basically says, person born in matches any two vertices. So match a person born in United States, lives in Europe. And so in this case, it's actually people born in the US who migrated to Europe, right? So I kind of got that wrong, which is why like understand the English first. Yeah. And then return the person name. So I just highlight here.
It is backed up by SQL again. Like, this is like if you want to perform graph optimized searches, then you probably go to this database, but then like use the query using graph query languages and stuff. But to actually randomly locate any node, maybe you have to go to rely on SQL again, because how do you know where is USA, right? Like if you have
So you should think of it this way, right? Like let's go back to the same example, right? In your org, someone is there, right? Your VP and the rate you guys are all there. The idea here is not to go identify you, try to query. Graph should be used where idea is to see interconnected relationship in a many-to-many relationship in a single table, if you will. Right? Let's say all the employees are stored in a single table for whatever reason in your org, right? Now you want to compare and contrast between all of them who has, whatever, let's say badges, a college and stuff like that. So in a SQL, if you want to be able to do that, right, it's not easy in a single table. If all your data is there in a single table, you want to compare and contrast, it's not easy in a SQL. And even it's not easy in a NoSQL either, right? So that's where graph comes in. Graph comes in to be able to compare and contrast on the data based on the properties across many-to-many relationship across different nodes, right? Not tables here.
Yeah.
Yeah, so, all right. So essentially with this query, right, it's just saying find any vertex that call it a person that meets any of the following conditions. And then they say born into some vertex. And then within that vertex, follow a chain, right? Go down, some algorithm for traversing until you get to the location graph, right? Or location vertex, I mean, and that should equal United States. So that's step one. Then step two, the same person vertex also has an outgoing lives in edge. So you need to follow that, traverse its edges until you reach another vertex of type location, whose name is property. For each person vertex, return the name property. So if you go back to the diagram here, then you're kind of doing it. If you were to do it just manually, you're kind of like saying, okay, follow this edge lives in until you find the country and then get the name, right? Then follow this edge born in until you find the country that they started in, right? United States, and then return the person. So that's kind of like probably how this query was written. And then Neo4j traverses, this giant graph. So let's see here. Basically, we like declarative languages. I think that's like the next part of this, right? Like I made a highlight. Nobody likes thinking imperatively. Even with that old, like imperative example in JavaScript, writing a bunch of for loops. I don't think anybody wants to do that with something as complicated as graphs. So, it's very important that whatever tool we have continues to use these declarative ideas and then hides kind of like that complexity that we were talking about. Like, right, you don't need to be a PhD to use this. We have a good optimizer to choose the best strategy for executing this query, right? Because there are many different ways of executing the query. So you could have, again, right, you could have many different types of implementations to do that, right? You could make for loops or while loops. But again, we don't want to do that. We don't want to have to start thinking about that. We want to just kind of like say, here's what we hope that we can achieve, and you decide the best implementation for it. So we got past this section, which was property graphs. The next section is GraphQL, graph queries in SQL. Although, and GraphQL is actually nothing like graph queries in SQL, but you might want to just look at that anyway. If you're like, what is GraphQL? I kind of feel like maybe this might be an interesting thing to go back and look at as well, if you're doing front end. And see how it relates to this.
Is this what Facebook was using? Is that what? Oh, that is open graph or something, right?
Yeah. So what GraphQL makes it easy to do is explore, again, like graph kind of relationships. This is like more modern as a tool, but then it also gives you an ability to make a simpler API. So you don't have to return, like one of the biggest problems with doing a REST API is that you'll make a curl call and get back all the data from that curl call, right? And some of that data you may not actually need. You may just need specific things like, I just need the name. I don't care about everything else in the API query, but I know I have to hit this endpoint and get everything back. And so what Facebook found was that like in building, like their mobile applications, especially, like as they started going out into the world, right? And people like all over the world started using, their application. especially like India, right, where people didn't have like faster speeds for a while. Now I think they do. But if you have like 3G speed, that API curl call is going to fail. So they wanted shorter API calls. And so that's kind of where GraphQL came from. You get like quicker.
So yeah, I mean, going back to the whole service as well. So microservice, whatever it is, like when you expose a service, the idea is to be a shared service, right, for a particular entity and stuff across org or group and stuff. If you want to shove too much information in the payload, your query and the latency is going to get impacted because it's going to travel through the network, whoever is accessing from where or whatnot. Basically, it's like, you know, think of GraphQL was invented to solve a different problem rather than just asking, okay, I need first name, last name in the service, right? Split as first name and last name, or I need like age and stuff. So every time you need a requirement was there. So the team that's deploying these services, they have to iterate it, add that element, and like expose it in the payload, right? So now going back to why GraphQL, they expose all the data elements for that model. Now you as a user, whoever is calling that particular API or a service, you can query specific elements that you really want in an optimized way. Let's say I just need first name and last name. I don't need, there are like 1,000 elements in the payload. I will just need 10. I can just specifically ask 10 and get that information from it. So think of it like an abstraction of schema on top of services itself.
Mm-hmm.
So this helps mobile or other IoTs, everything to ask only what they need rather than consuming the whole payload and neglect some kind of elements. So it's
I didn't it's good to know. So because with NoSQL databases, right? So what happens is when you are loading a record, right? So usually if it has a dependency on some other, you want to populate that record with information from some other table. So if you are like what Vijay and Karthik were saying, so if you have to fetch, like let's say profile, right? If you are trying to fetch a profile and that profile record depends on information from other tables. So what happens, so that's what I was talking, right? There is this hot partition, like if there are lots of profiles in one account and you try to get the profiles of lot of profiles, basically if enterprise customers usually have a lot of profiles, if you're trying to fetch them, this because for every profile fetch, the account, the single record is getting loaded, even though it's not necessary information. All I care is like what license they have. But because it's a REST API, I have to return the entire profile information. And kind of the load gets spills over to the other tables. So I think this is a nice thing to know. Maybe there's some.
There is a tremendous amount of complexity involved, right? Yeah, like think of it this way, right? On top, you need to run a separate GraphQL server, right? Now you are exposing your API, let's say REST API through just an example, probably some service abstraction, right? Like API gateway or whatever, even service mesh if it's internal east-west traffic. But the minute GraphQL comes into play, then another layer of abstraction, right? There is another server sitting in between all your, right, yeah. So, which is like another layer of server sitting in between all your services behind the scene, which is connected to it. And then instead of the actual callee who is like trying to talk to your API gateway, they'll talk to the GraphQL now, right?
Correct, yeah.
So it's another hop, another latency involved, but it solves a different problem, right? So.
Yeah, so not really reducing the server workload. It's just reducing the network payload size.
That's right. That's right.
Correct. Yeah, network payload would be reduced. Yeah, because at the end of the day, your data service still has to do what it has to do, right?
Right.
It still has to execute, and I used to work like way before, almost 2009 on a concept called SQL pushdown from XQuery that used to go push it down. There are some engines where it pushes it down the query to database level and then get only needed information. But this is a little bit different where this is again an abstraction across all your data services across the org. So anyone needs anything, they should be able to specifically ask that that particular query. And if you go a little advanced, let's say you have profile REST API as exposed, and then you have some other API exposed as well, right? Now, GraphQL can go and liaise between these two API calls, get those two payloads, and then filter and only needed information it can send it back, right? It can do that too, not only on a single API call. Yeah.
Yeah,
Good
I think
stuff.
for WhatsApp or something else, like what you're saying, like in a place like in India where you don't have a lot of network bandwidth at your disposal, maybe, yeah.
Yeah, and I know in India everybody uses WhatsApp, so you have to have like a good. I mean, that's why like Facebook and WhatsApp are so popular there. It's just because like Facebook, the team did an excellent job, just like making their service really work. And so now, like because of that, India is like one of the biggest users of Facebook, you know, and so that's like billions of people, right? Like, and that means more eyes and more advertising. So it works, right? It works too well, probably. So that's how you make money. All right, so we're getting close to the end of our time here, but I guess like we're doing pretty well. I think like we're almost there. So I would just kind of say, you know, last here, right? Like we're gonna look at graph queries in SQL next. How like it's more complicated than Cypher, as you can tell. It's the same example of trying to like go and traverse a graph. So you can see in the USA of vertex IDs of all locations within the United States. So select vertex ID from vertices where properties equals name United States, union select. I mean, like when I was working at RadNet, right, I was working with this thing called Oracle SQL, like for Apex on the web, right? And we had like this giant medical database that, you know, was just, it was like lines and lines and lines and lines of SQL that just eventually became like so ugly to read that it was like a pain. Like I was just like all day like reading unions and trying to understand what was going on and like procedures and triggers and events and all that stuff. And it was really hard to kind of like go through, but you can tell, I guess, like that's my point, right? Like sometimes like when you're trying to do stuff in SQL, it can get really ugly and hairy really fast. So that might be the time to start asking, maybe we need another tool, you know? But yeah, we'll come back and check this out next week. So in the meantime, feel free to read up. And then if you feel like we want to read chapter 3, let's go to chapter 3 as well. And that's all I got. I see like people have to drop. So I'll see you later. See you, Karthik, as well.
All right, guys. Yeah, I try to find the mute button and then sometimes it just gets stuck. So.
Oh, okay. All right. Yeah, no worries. Yeah, I'll talk to you later and talk to you on Discord. All right.
All right. Sounds good, guys.
All right. See you.